introduction, and thanks to all the organizers for inviting me to give a talk. Today I will talk about this paper, which we recently put out with Ilya Buric, Francesco Russo, Volker Schomerus, who's my supervisor, and Alessandro Vichi. And for some more detail, you could also look at this previous paper by the rest of the authors of the last year. So the setting of the talk is that of conformal field theory at finite temperature. And as all of you know, when we consider CFT at finite temperature, we interpret the correlation function as traces over the Hilbert space of the theory, weighted by the thermal density matrix. And if we work in Euclidean time, we can interpret this trace as the time direction being compactified on a thermal circle. For the other spatial direction, however, there are many choices that we can make. The simplest one, and also probably the most studied, is the one where the spatial directions are just flat space. And in this case, the geometry is described just by the temperature as parameter, or inverse temperature. And in this setting, the correlation function, in particular, are simpler. In particular, the one-point function are completely fixed by symmetries, to the point that the one-point function of a scalar is of this very simple form here. Another very natural choice, which is the one we will do for the rest of the talk, is the one where also the spatial direction are compactified on a sphere. In this case, the parameters that describe the geometry are more, as we can allow also for twists along the sphere. And so we have a temperature and then some chemical potentials. This additional structure means that the one-point function in this case are not fully fixed by symmetry. So in some sense, the theory is more complicated to analyze. However, this additional complication we can see also as a tool to resolve the information about the theory with more detail. Maybe just a last comment about our choice of geometry is that if we consider the 2D case, this is the familiar case of the torus, for which many results are already known. For instance, one of the most famous one is the Cardis formula for the density of primaries. In our case, however, we will focus in 3 dimensions. So the geometry is the thermal circles times the sphere. In this case, the conformal group has 2 Cartan generator, the dilatation, and one of the rotation generator on the sphere. And so we have 2 associated parameters, the inverse temperature and 1 chemical potential. And we have the freedom when we define our correlation function to put both these Cartan generators inside the trace. And so this is also what we do. Here, Q and Y are just the exponential of the beta and mu. Another comment is that for the insertion points of the fields, thanks to the conformal mapping of the cylinder to the plane, we can actually parameterize the coordinates of the fields with the usual polar coordinates in the 3D plane. For the rest of the talk, we will focus in the simplest possible correlation function, which is the one-point function of a scalar field. As I've already mentioned, this is not completely fixed by symmetries. However, word identities do reduce the dependence of this object in the different variables, and in particular, they imply that the one-point function depends on the insertion points on the field just through this s variable, which is the sine squared of the angle with respect to the axis of rotation of the generator that we have chosen. As usual, we can decompose this correlation function in conformal blocks, thermal blocks in this case, which we can imagine to represent in this form, as the different blocks represent different contribution of the conformal families to our thermal trace. And this conformal block decomposition allows us in principle to access this type of coefficient, so the one of which involve the external field, the scalar, and 2 identical operators. However, in this setting, these conformal blocks are actually not known in an exact form, apart from the very particular case where both the external and also the internal field are scalar and the chemical potential is turned off. So in general, we don't know much about these conformal blocks. So the question which we will try to analyze for the rest of the talk is how much information can we actually get about this OP coefficient from the knowledge of the one-point function, provided the fact that we don't know an exact form for these blocks. And maybe I can already give a preview of what will be the final answer. And the final answer, in some sense, is that we can actually extract a lot of information about the OP data. And in particular, the low temperature behavior of the one-point function can allow us to extract exact data for the OP coefficient with the light exchange operator. And instead, the high temperature behavior of the one-point function will allow us to derive asymptotic formulas that describe the regime where the exchange operator is heavy. In order to arrive to this type of picture, this is the plan of which I will follow for the rest of the talk. I will start by discussing the Casimir equation that the blocks satisfy and their boundary condition. Then I will move to consider expansion for blocks at low temperature and how we can use those to extract information about low-lying OP data. We will then move to the opposite regime in some sense and see how to derive inversion formulas for OP coefficient thanks to orthogonality of blocks and see how we can use these inversion formulas to find asymptotics for OP data. In the end, I will conclude by, in some sense, testing all these analytical results in the simplest case that we can imagine, so the free theory. If there are any questions, maybe this is a good point before I start. Okay, if not, maybe I can start by discussing the Casimir equation. Here I put the precise definition of the one-point thermal block, which is just the one-point function with a projector to the conformal representation of a certain operator, certain primary field inside the trace. And we also strip off this prefactor that we know is fixed from word identities. So our conformal blocks is fully specified by this set of quantum numbers, those of the exchange operator that we just call delta and L. Then there is the scaling dimension of the external operator, delta phi. And then there is an additional label, which we call tensor structure label, which one can regard as an additional label that distinguishes the block which share the same other quantum numbers and is related basically to the tensor structure label of usual three-point function in flat space through the limit at 0 temperature. But okay, I will not say a lot about this. To derive the Casimir equation, what one does is to insert the Casimir operator inside the trace and make it commute past all the operators. And in this way, one finds a differential equation, which here I've put in a very schematic form. We have here the Casimir eigenvalue in the representation of the exchange field. And here on the left, we have the actual differential operator, this C delta phi, which is a complicated second-order partial differential operator in the three variables, Q, Y, and S. What is important is that this Casimir equation actually completely fixes the blocks if paired with some boundary condition at 0 temperature. We are not able to exactly solve this Casimir equation, and so find an exact form for the blocks. However, the important point is that still this Casimir equation can give us really a lot of information about these blocks. Let's specify straight away our choice of boundary condition. If we expand the block at around Q equals 0, so low temperature, and we are actually able to solve the differential equation at lowest order in Q. And so in this way, we can find an exact solution for the boundary condition of the block. We see that this solution space has L plus 1 is L plus 1 dimensional. So A, this tensor structure index runs from 0 to L. And in principle, obviously, one can choose different bases for this space of solution. But we will choose this particular one. Here P are Jacobi polynomials. A feature of this choice of basis is that is factorized in the variable u, which is basically a rewriting of y, so is related to the chemical potential, and s, which is the position variable. And the reason why we choose this particular basis of solution will be clear in a moment. So for the moment, we leave this choice as just a special choice. Now that we have fixed the boundary condition at q equals 0, we can actually take this opportunity to see that we can extend this solution around q equals 0. If we expand, in fact, the block not only in q around 0, but also in the other two variables, so u and s, we can transform the Casimir equation into a set of recursion relation for the coefficients that appear in this expansion. The recursion relations are quite involved. They involve many terms. However, by fixing the boundary condition, by imposing compatibility with our choice of basis, and by using a particular order of solution for this recursion relation, we are actually able to solve all these, in a recursive way, all these coefficients. And so in this way, extract a low temperature expansion for these blocks. This already solves, in some sense, half of our problem. The half regarding the low temperature and the exact OP coefficient. In fact, if we know a one-point function in this geometry, we can expand the one-point function at low temperature, match this expansion with this one we have from blocks, and extract exact data about the OP coefficient. The reason why this is made possible is that this low temperature expansion, if you see, starts with q to the delta. So heavier operators start to contribute later in this expansion. One can actually disentangle one operator with respect to the other. Maybe one comment at this point is that conformal blocks are specified in terms of the quantum numbers of the exchange operator, while here the sum runs over the single primaries. So actually, with all this type of extraction procedure, what we can actually extract is not the single operators, but the sum of all the operators, or the average of all the operators which share the same quantum numbers. Okay, so half of in some sense, of the plan is already done. And now we can come back to why our choice of basis for blocks is special. And to do so, we may take a step back and consider not the one-point block, but the zero-point block, so the conformal characters, for which an exact formula is known and is very simple. Why this is instructive for us? Because one can actually explicitly check that the conformal characters are orthogonal in the beta and mu space if we choose an appropriate choice of inner product, which is of this form here, and the measure is of this quite simple form here. One then can move on to the one-point blocks, the one we care most. And also in this case, one can infer that actually should exist a similar type of inner product which makes blocks orthogonal. And once again is the Casimir equation which comes to help. In fact, if we demand these inner products to be symmetric with respect to the action of the Casimir, we can find an inner product for which we expect the block to be orthogonal if we work in an appropriate choice of basis for the blocks. The measure that we find in this case is basically the same as for the characters, apart for a factor which depends on the insertion points of the field. And here comes why our basis of tensor structure that I showed you before is special. This is precisely because one can check that in this choice of basis, the blocks become orthogonal with respect to this inner product. Orthogonality is very handy because we can use it to invert the block decomposition of the one-point function. In fact, we can imagine to sum not over the single primary fields, but instead over their quantum numbers. So here we integrate over the dimension and sum over spin. and the sum over the tensor structure. And then we can use orthogonality to invert this relation and find a formula for the average value of the OP coefficient, which share the same quantum number for the exchange operator, in terms of the one-point function. In a very similar way, from the orthogonality of characters that I showed you before, one can find an inversion formula for the density of primary states. This is somewhat more standard. What is important for us is that these integral formulas are, despite being quite complicated, especially the one for the OP coefficient, as here we have something which we don't even know exactly, like the blocks. Still, we can use this integral representation to find information about the CFT data at large value of the dimension of the exchange field. So when the field becomes heavy. To see how this is done, maybe I start by commenting the case of the density of primaries, which is simpler. And in this case, this is our integral representation. And inside this integral, we have the measure that we know exactly. There are the characters, which we also know exactly, and then there is the partition function. And one can infer that when we make the dimension delta large, this integral is actually dominated by the high temperature region. So beta goes to 0, mu goes to 0, while the ratio omega is kept finite. And so what we can do for the partition function is use an high temperature expansion for this object. In this case, there is the results coming from the thermal effective action, which precisely gives us a formula for the high temperature expansion of Z. In the case, our CFT is gapped when we compactify on the thermal circle. This is the result that comes from the thermal EFT. We see that the most singular term depends on the free energy of the theory, and then all the other terms depends on more and more EFT coefficient, C1, C2, C3, and so on. Now that we have a formula also for our partition function, we can actually perform the integration doing a saddle point type of analysis and obtain an asymptotic expansion for the density of state for a gap theory for large values of delta. And this is the type of formula that one gets. There is an overall leading behavior, which is a power law times an exponential, and then there are all these correction, which goes as delta which goes in power of delta to the minus 1/3. And as you see, they depend on more and more EFT coefficients. This holds for a gap theory. The free theory actually falls out of or from this description, because when you compactify it on the sphere as a gapless sector, so when we will check all the formula in the free theory, they will be slightly different, but the strategy is the same. So then I will show how this formula is adapted in the case of the free theory. Okay, let's now move on to the case of OP coefficients. In this case, the integral representation for the OP coefficient is more complicated, as we have the measure that we know exactly, but then there is the partition function, there is the one-point function, and there are the blocks. So for the partition function and the one-point function, we can use high temperature expansion in the same way we did in the case of the density of primaries. In particular, for Z, we can use the same high temperature expansion, while for the one-point function, we assume an high temperature expansion of this type. This type of expansion is motivated, the singularity structure in beta is motivated by the limit to the plane. In fact, sending beta to 0 is equivalent to sending the radial direction of the sphere to infinity. And so we expect this type of singularity 1 over beta to the delta phi to be the leading singularity in beta. Instead, the dependence on omega and S, we assume to be this one to have compatibility with our block expansion at low temperature. In particular, you see that the dependence on omega is just in even powers of omega. And this function, b of s, are polynomial in S with power which is bounded by the power of omega. So the first term here is just the usual constant term, which people call b phi. And then this is a linear term, this is a quadratic term, and so on. So this is the type of structure that we have for the 1-point function. Then there is the last piece inside of the integral, which is the block. And once again is the Casimir equation that comes to help us. In fact, all the delta dependence of this integral sits inside of the block. So what we search is we search for a large delta expansion of the block. And once again is the Casimir equation that provides us this type of expansion. In fact, it was already observed in this previous paper that if one extract from the block the simple prefactor q to the delta, the Casimir equation becomes no more quadratic in delta, but actually linear. And assume this simple form, where you can see that the term which is linear in delta is actually a simple first-order differential operator. There is just a single derivative in Q here. And then this is more complicated, this other differential operator. This means that if we expand our block in inverse powers of delta, we can use this type of differential equation to solve recursively for the coefficient in the expansion, order by order. And each time that we solve, we just have to solve a linear differential equation in terms of just a derivative in Q here. To fix the integration constant that we require compatibility with the low temperature limit. Okay, so now that we have all the ingredients inside our integral, we can actually evaluate it, and we use the same strategy that we used for the density, so a saddle point type of expansion. And in this way, we can find an asymptotic formula for our OP coefficient, in the case the theory is gapped. And this is the leading term of the series. We see that we have EFT coefficient coming from the 1-point function. Then there is this general global scaling, which depends on the dimension of the external field, delta over delta phi over 3. Then this is a constant. And then we have this additional scaling, which depends on the tensor structure label of the block. And you see that the higher is the value of the tensor structure label, the higher the behavior of the OP coefficient is suppressed, to the point that if the dimension of the external field is low enough, we can have that some OP coefficient grow and some decay when we go to delta very large. So this is why we call this a hierarchy of tensor structure. If we focus on the case A equal to 0, so the dominant one of this OP coefficient, our result recovers what was already known from ETH, and also some ETH, the Eigenstate thermalization hypothesis, and also some other related studies that were done previously. An important comment, however, is that through this method, one can also find not only the leading behavior, but also the correction to this formula, which will depend on more and more EFT coefficients. And a second small comment is, as before, this formula holds in the case of a gapped theory, while in free theory, there is a slightly different formula, still for the fact that, for instance, also here, the 1-point function, the limit of the 1-point function at high temperature is slightly different in free theory with respect to a gapped theory. But the type of reasoning is the same. Okay, so at this point, I would go to see how all these results apply in the case of the free boson, unless maybe there is any question.
So can you specify a bit better with this matching or not matching with ETH? So you said A equal to 0, match ETH prediction.
Yes.
But this means higher tensor structure do not match?
It's not they do not match, is that the ETH basis, the basis of tensor structure that people use is in ETH is another one where these other bases contains basically the same amount of our dominant tensor structure. So the leading behavior of the OP coefficient in that basis all go as our highest scaling, because all the other corrections are somehow hidden inside the other term that we in some sense separate by using this type of this type of basis.
I see. So in some
It's
sense,
like
the ETH prediction is 0 basically for them, in this sense.
the ETH prediction predicts that all the OP coefficient in all tensor structure go like the A equals 0 tensor structure. So they all go like delta to delta phi over 3. And this is why basically, and this is due to the fact that the choice of basis for the OP coefficient is such that all the terms in the ETH basis contains the same amount of our dominant dominant, in the sense you can also take this formula here and then change basis. And if you choose a basis which contains the same amount of the dominant tensor structure equals 0, then the leading behavior will always be this one, and then this other one will appear as corrections.
I see. Okay, thank you.
Okay, so maybe now I can comment about the free boson. In this case, the Hilbert space of the theory is very simple, as is just the Fock space built over the Hilbert space of the single particle associated to the field phi. And so we can easily find a formula for the partition function in this form here, where you see that this term here comes from summing the geometric series, and then the rest is the Hilbert space of the single particle. And then one can massage this formula into this other form, which is slightly better for our purposes. And then we can start applying all the reasoning we have done in the previous discussion. We can look at the low temperature expansion of this partition function and use it to extract, in this case, exact information about the spectrum of primaries by matching this expansion with the one of characters. So in this way, we can extract exactly information about the multiplicity of primaries appearing in the theory. Here on the right, I've put, for instance, the plot in the case of scalar primaries, but one can do also obviously for the others. And instead, if we move on to the opposite regime, the one of high temperature, from all the discussion that we've done before, we know that this allows us to extract the asymptotic behaviors of the spectrum of the theory. So what we want to do is to find an high temperature expansion of our free theory partition function. And to this purpose, we can observe that our formula for the log of Z free is of a very simple type. In fact, it can be expressed just as a series over the same function f, just with a rescaled value for the temperature. And the asymptotics of this type of series is actually something which is already known in literature. In fact, there are some standard results that tells you that if you have a function which you can represent which is of this type, so it's just a series over another function with the rescaled value of the parameter, you can infer the asymptotic behavior of the function when beta goes to 0 from the one of the function inside of the series. So I will not give the details here, but this is the method that we use. And in this way, we can actually find an all order high temperature expansion for the partition function, which reads like this one that I put here. We have the most singular term that is the one we also expect for a gap theory, and from this one we can read off the free energy. However, the next term, which would be a constant in a gap theory, is instead here a log, and this is precisely the contribution coming from the gapless sector, which is present in the free theory. So in this case, we have to adapt a little bit the analysis of the inversion formula to accommodate for this log, but the strategy is basically the same. And in the end, we get a formula for the density of primaries in free theory, which is of this type. The main difference, I've highlighted the main difference with respect to the gapped case. There is a slightly different overall scaling, this plus 1/12, and then there are some logs appearing in the correction. What is important, however, is that this formula is completely specified. There are no unknown coefficient, and in principle, we can go to any order that we desire. Now that we have the asymptotic formula fully specified and also the exact data, we can actually test how good are these asymptotic formula by plotting the ratio of the exact data with respect to our asymptotic formula. Here we actually plot the log, and this is for scalar primaries. Maybe you should focus on the plot on the left. The darker the curve means more and more term in our asymptotic expansion. And the plot here on the right is basically just a zoom on these two lower curves here of the plot on the left. We can see that by including more and more order, the asymptotic formula becomes better and better. And actually reach a quite good agreement with our data. In particular, if we look at the errors, we see that just the asymptotic formula with just the leading term has an error of 40%. But if we include more and more terms, for instance, here is 7 terms in the asymptotic formula, we can improve by an order of 10 to the 3. So a pretty big improvement. Maybe I can take this opportunity to say a comment coming from this plot is that people have already studied this asymptotic formula for the density of primaries, but mostly focused on the leading term of this series. But from at least from this type of matching with the data in free theory, we see that actually the correction are pretty important if one wants to see a good accuracy with exact data. So let's now move on to the more interesting case of the one-point function. And in this case, we will focus to the simplest non-trivial one-point function, which is the one of phi squared. We can obtain a formula for this one-point function by taking the OP from the two-point function of phi, and we obtain a formula of this type here. And now that we have a formula for the thermal one-point function, we can apply all the discussion that we have done concerning the OP coefficient previously. In particular, we can expand the one-point function at low temperature and match this low temperature expansion with the one of blocks coming from the recursion relation to extract exact data for the OP coefficients. The result of this procedure is of the type here as the one I put here on the right. This is for a spin to exchange. So we have 3 values for the tensor structure, A, 0, 1, and 2. And already we see that the A equal to 0, 1 is growing, while the other 2 are decaying. So this already is a good sign of the expectation we had. However, if we want to have a precise control over the asymptotics, what we have to look is into the high temperature expansion of our one-point function. Once again, we see that our formula for the one-point function falls in the same category that we already seen also for the partition function. In the sense, this is also a series of the same function with just a shifted value of the temperature, and so we can apply the same theory for the series of this type to infer the high temperature expansion of the one-point function. And we find an expansion which is like this type here. In particular, we see that there is a 1 over beta term, which is the one that we would expect also for a gaps theory. This is the 1 over beta to the delta phi. That we have the high temperature expansion of the one-point function. We can adapt the analysis of the inversion formula for the OP coefficients to this case and get asymptotic formulas for the OP coefficient for the free theory. The formulas are similar to the one of the gaps theory, Again, there are some logs, some log behavior appearing in the formula. But what is important is that these formulas are completely fixed now that we know all the FT coefficient contained in the 1-point function. So we know everything that is inside this formula, and we, in principle, can also compute more and more corrections here. We can now compare these asymptotic formulas with the exact data that we derived by looking at the expansion at low temperature. This slide here is about the dominant tensor structure, so the one with A equals 0. Here on the left is the case of spin 0 exchange. At these low values, in some sense, low values, it's still delta equal 30. It's not very good to match the data. So ATH, this value is not very good. But going for the spin of the exchange field, so here I plot spin 0, 1, and 2. From the exact data, we see that the asymptotics tend to be independent of the spin. And this is a feature that we also observe in our asymptotic formula, at least in the case of A equals 0, that if we look also at the correction of the formula, at least to the order that we've looked, we same thing also for the other tensor structure, even though the situation becomes more and more complicated as the blocks going higher values of A becomes more and more complicated function. Here I put the plots of the exact data in the case of spin 6 exchange. So we expect 7 tensor structure. A goes from 0 to the spin, so 6. There is the dominant one, which is out of the plot, so it's not shown here. And then of the other 6 lines, curves, we have chosen to represent only some of them. And in particular, this yellow one, we find a good agreement with the data. Okay, so I may already summarize the discussion. I've shown how to use the thermal 1-point function on the fully compact thermal geometry, so S1 times S2, to extract information about OP coefficient across all the spectrum of exchange operators. In order to do so, we had to advance the theory of the associated 1-point thermal 1-point function, allows us to find the asymptotic expansion for the OP coefficient when the exchange operator becomes heavy. And this is done thanks to an inversion formula for the OP coefficient and the control of the blocks in the regime where the dimension of the exchange operator becomes large. Maybe a last comment about this is that all the result of the blocks have been basically derived just from their Casimir equation, which once again provide us with a lot of information, despite we are not able to solve it exactly. I may conclude with some outlooks of this discussion. The first one is that we've tested our analytic result here in the case, the simplest case, the one of the free boson. But the same can be done in any CFT where the thermal 1-point function in this geometry can be computed, at least in the two regime of low and high temperature. And we have some work in progress on holographic CFTs, to check this formula in holographic CFTs. Then another natural expansion would be to extend this analysis to spinning external fields. This was just scalar external. And in this way, we would be able to access, for instance, the OP coefficient of the stress tensor. Then I put here two, in some sense, far-reaching outlooks. One is to see if we can use the inversion formula to probe other asymptotic regime of OP coefficients. For instance, we could consider to make also the external operator heavy, so large. And there already exist some results about this heavy OP coefficient in literature, and we could try and see if we reproduce them. Also related to this, in 2D, there is actually a single formula that unifies all the different regimes for OP coefficient, and could be interesting to see if one can find the same also in 3D. And a final, more broad goal could be to study the conformal block expansion, not only of one-point function, but also of higher point function in this compact geometry. This obviously is more complicated. However, a hand could come from a connection with the integrability, something that already exists at zero temperature, and we are working to extend also in the case at non-zero temperature. Thank you very much.
Thank you, Francesco.